Hello and welcome to another video. In this video we're going to be working on count pairs of connectable servers in a weighted tree network from the contest 125. This is the third problem. And in this problem you're given an unrooted tree with n vertices representing servers numbered from 0 to n-1 and an array edges where you have a, b, and weight. And there's a bidirectional edge between a and b of weight, and you're also given an integer signal speed. Two servers are connectable through the third server if a is less than b, a does not equal c, and b does not equal c. The distance from c to a is divisible by signal speed, and the distance from c to b is divisible by signal speed. The path from c to b and the path from c to a do not share any edges. Return an integer count of length n, where count I is the number of server pairs that are connectable through the server. So let's go through the examples. So basically, in the first one, they tell you that since signal speed is 1, you basically have to return an array for every single server as if it was server C. So if this was server C, how many servers can it connect? It can't connect anything because if you go from here to something, every node along this path will share this edge. So none of these are connectable. For the next one, if this was server C, you can connect 0 with any one of these. So that's 4 connections you can make. So you can connect like 0 and 2, 0, 3, 0, 4, 0, 5. For the next one, if this was server C, you can connect any one of these two with any one of these three. So that's 6 total combinations, right? So like 0, 3, 0, 4, 0, 5, 1, 3, 1, 4, 1, 5. Then for the next one, same kind of thing. So 3 and 2, so you get 6. 4 and 1, so you get 4. And then 0 here, because everything shares this edge. So this is what you want to return. So let's go through this one in more detail, and let's just go through this one in more detail, because this is the one that we're going to use to actually figure out what to do in this problem, and like how to do this. So essentially what we can do, and also take a look at the constraints. The constraints are 1,000, which means if you do like a BFS or a DFS from every single node, like that will pass, right? So if you let's say you BFS from this node, that will take order n, right? And so if you BFS from every single node, you will get an n squared solution, and n's only 1,000, so that's fine. So that's kind of the idea we're going to have here. Is notice that for any node, like let's say we can just arbitrarily pick nodes as node C. Let's say you pick this one. We know that, let's take a look at the paths coming out of this node. We know that like anything on this path starting here is not going to be connectable because everything is going to share this edge right here, right? So there can be like a whole tree over here, but you can't connect anything in here to each other because they're all going to share this edge. So that's the main idea for this problem. Is for every single node, we can write this down. For every node, let's take all paths from it and get how many valid nodes we have. So I think let's take a look at what this example is for the second problem. It is signal speed is 3, so let's just call that like S. So essentially, let's just walk through a couple of these. Like let's say we have this node here, and let's actually ideally try to actually do this and then cut it and do this. Okay, there we go. So for this node here, let's just say this was node C. Basically, what we'd have to do is we can just BFS in every single path we can. So we can make a different BFS in like this path, a different BFS in this path. And for every single path, we can just count out how many valid nodes we actually have, right? So for like, if this was C, we would go along this path, just a basic BFS, like for every child in the in this node, let's do a BFS. So we're going to BFS over here with length 3. And then we're going to BFS over here with length 6. So both of these nodes are then like valid nodes to connect to something else. So we don't really care actually what these nodes are, like as long as we know how many there are. So there's 2 nodes that are like valid to connect to something else, right? This node and this node. So here we're going to write, we have 2 nodes on this path. Then let's take a look at the other path. There's only one other path, right? So if we go down this path, this node is not valid because it needs to be divisible by 3. This is only 1. So we come over here, this total path is length 3, so node 4 is valid. So this is 1. And let's come over here, so this is length 8 altogether, so that's not valid. And this is length 7, so this is not valid. So the only node that was valid was node 4, which means on the first path, we have 1 node, or 2 nodes, right, on this like left path, 6 and 3. And on the second path, we have 1 node. And if you look at these examples, a node can have a bunch of different edges. So like just because this has 2 paths, like a node can technically have like a ton of paths coming out of it. So you have to do this for every single path. So essentially what you will get then is you will get an array of numbers, right? So you'll get an array of numbers, and each number represents like all the nodes in that one path that were valid. And let's say, so for this example, it's pretty easy, right? We can connect any one of these 2 nodes to this node. So there are 2 solutions, right? We can do like 4, 5, and 4, 6. So let's take a look at the answer for that particular node. So if we use 0 as the output as node C, we do have 2. Now let's say we have, like I said, we can technically have a lot of different starting points, right? So we're going to BFS from every single starting point as node C. So that was the example of using node 0 as node C. What if we use like this node as node C? Let's take a look at all the paths. So this is the first path. So it has, this is not valid because this is only 1. This is 4. This is 7. So none of these are valid. Then here this is 2, not valid. 7, not valid. 6 is valid. So we only have 1 node, but we don't have any other like chunks to connect it to, right? So there's nothing there. So let's actually change this wording, and instead of signal being 3, let's see what happens if signal was 1. And this is kind of like how you do this. Like this is basically going to explain how to do this problem. So let's say signal was 1. Now we know that for signal 1, any node is valid in any path, right? Like this node would be valid because everything's divisible by 1. So let's walk through what would happen if this was C with a signal of 1, and then you can basically just apply this to every other node and get a solution. Okay. So let's start with the first path. So the first path, every single node will be valid. So all of these are valid. So we have 3 nodes here. So we're going to write 3. Then the second path, there's 1 node. 1, then 1, then 1, right? These are all the different chunks. So none of the 3 in here can be connectable to each other, but they can be connected to other things. And the way we're going to do this is we're actually going to have duplicates. But we can easily get rid of that. So for example, we'll say like 6 and 4 is a connection. And 4 and 6 is a connection as well. But then we'll just we'll get all the combinations and just divide by 2 to get rid of that, right? So we'll get every single pair combination, but then we'll just divide by 2. So this is a chunk of 3, chunk of 1, chunk of 2, chunk of 1. And basically, for every single one of these nodes, like let's say we pick this node, we can connect it to any node that's not in its own chunk. So what we can do is we can get a total here. So total 6. And for every node, so there are 3 nodes in here. So for each one of these, we can connect it to every node that's not in its own chunk. And how many nodes aren't in its chunk is just the total minus the nodes in that chunk, right? So the total is 6 nodes and this is 3. So for every one of these, we can connect it to every one of these. So this is 3 by 3 plus. Then for every node in this chunk, we can connect it to every node that's not in this chunk, which would just be 1 times 5, right? Because this node can be connected to any one of these 3 or any one of these 2, as long as it's not in its chunk, because every node, like I said before, every node in the chunk can't be connected to every other node in the chunk because they will all share this starting path. But once this starting node is different, once the starting path is different, then none of these share any edges, right? So the way to check for things have edges is pretty easy. Just for every node, just do a BFS for every child, do like a separate one. Yeah, so this node will be connected to 5 plus, now this node can also be connected to 5, right? Like 1, 2, 3, 4, 5. So 5, and then last node also connected to 5. And like I said, we will get duplicates because technically, like when we connected this node to all of these, we also connected all of these to this node, right? So we'll basically get like duplicates of like 0, 4, and 4, 0. And the way to get rid of duplicates, really easy. Just take your total here. So we got 15 plus 6. Oh, sorry. This should never be odd. That's why I was kind of confused. It was 24. So we have 24 connections, but half of them are duplicates because, like I said, if we're connecting these to this and we're connecting this to this as well, we're going to have duplicates. So we just divide by 2 and we have 12. So if signal was 1 for this node as the center, we would have 12 different connections. And then you just do the same thing for every single node. So you just take every single node, you BFS through every single child as like a unique BFS. So this would be like 1 BFS, this would be 1 BFS, 1 BFS, and so on. And it's totally fine, right? Because we can split our BFS down. We can split it up into multiple chunks, and the whole like length of all those BFSs combined will be the entire graph, which is fine because that would still give you an n-squared solution. But yeah, it's the main intuition for it. So let's take a look at the code. I don't have this. Okay, so we make a graph, just a basic graph. So for every node, you just append every node that it's connected to with an edge and the distance. Then for every single node, so the other thing I didn't mention is, let's say every single node we're going to pick as our C value, but if there's only one edge from the node, it's not possible to connect anything, right? Because you have to have at least 2 chunks to connect nodes. So like here, this only has 1 edge. So this will all be 1 chunk, and then there's nothing to connect it to anywhere else. So that's what we're doing here, is we're just checking if there's only one edge from the node, then it's not possible to do anything. Then this is like I called it paths, but this is like chunks. Then we BFS from every single child node. We get a total of how many valid nodes we visited. We make a visited set, where the other thing is you want to make sure, like, if you BFS this way, that you can't go back over here, right? So when I BFS, let's say I choose to BFS this way, I will mark this is visited and this is visited. So my starting node as my C and the node that I picked to BFS from. So that's just what I did here. Then just a basic BFS where you just append the child and the distance. Keep doing a BFS, and every node you visit, keep track of the distance, just standard BFS. When you get the distance, make sure, is it divisible by signal speed? If it is, add to my valid nodes. Then finally, at the very end of the loop, what you need to do is you need to take your take however valid nodes you have, add it to your paths array, and then this is where you do the thing that I showed you. So we take the total of our paths array for the node, and then for every single chunk, right, for every single chunk, the number of nodes we can visit from that chunk is the number of nodes in that chunk times the number of nodes everywhere else. And like I said, we'll get duplicates, so then we just divide it by 2 to get rid of our duplicates. And we can run this. And I'm not sure like what other people got as runtime, so maybe you could do better. Maybe like DFS works better. Maybe you could even like do this somehow in an N, like an O of N solution, not sure. But this is what I came up with. So curious if someone came up with something better, or if it's possible, let me know. But yeah, so for the time here, this will be O of N squared. And the space will be, so let's take a look at what we use. So we have the graph. So technically there's only n edges maximum. So I'd say for that, that's like O of N. Because it has to be like a valid tree. In the BFS, also O of N maximum, visited set, O of N maximum. So I think this is just O of N, paths also O of N maximum. So yeah, I think this is just O of N and O of N squared. Yeah, I think this is a pretty good problem. And yeah, if you have any questions, as always, ask in the comments. And if you did like this video, please like it and please subscribe to the channel, and I'll see you next one. Thanks for watching.